Hi folks, in this lesson we're going to look at the force on a current carrying conductor when placed in a magnetic field. Now this is something that's a little bit familiar, or should be a little bit familiar to you with the work that you did in particles and waves in higher physics, where we were using our left and right hand rules, and we had a charged particle, an electron or a proton entering a magnetic field when we were looking at particle accelerators. But what we're actually going to do, we're going to quantify the force that this particle will experience, or indeed that a wire will experience if placed in that magnetic field. So we'll go and look at the learning intentions, and then we'll get cracking. So here we have, I'm going to leave 13.21 alone for now. But if we look at 13.22, use appropriate relationships to solve problems with force, current, and magnetic induction. And then in 13.23, we'll have F is equal to ILB sine theta. And obviously your two force equations, these are for the F equals QVB is technically new to you in this unit, or in my unit, but Mr. Forward should have done F equals QVB in particles with you. Okay, so what we're going to do is I'm going to go through an experiment with you now. This experiment is on page 19 of the course notes. The rest of the work is on page 18 of the course notes, and so I'm going to skip ahead a little bit, but what we'll have basically is we will have a set of scales, just balances. And so there are our scales, and they'll read something on there. And then we will have, now this might be a bit tricky to draw. Ideally, I would like to be drawing it in 3D, but I'm not even going to attempt to do that. And so we'll have a horseshoe magnet. And so there we're going to set our magnet on top, and then we can reset the scales to 0, so we can tear the scales. And if we say north, south, now let me just show you here. So this is what I'm trying to draw here. Set of scales. We've got our horseshoe magnet, and then we're going to have a wire that's going to have a current passing through it. And so here we'll have our wire that's going to be passing through it. And let's see. If I'm going to do the wire a little bit bigger, and now that I've done that, I'm going to do that little dot thing. If you remember the sort of sign convention of current moving through a wire, what we'll have is we have, if this is our wire, and then this will be towards, and then we'll have that being away. So as it's drawn here, the current is going to be coming out of the page. It's going to be going up, or as if it would be coming towards you observing this from here. So obviously the scales have a mass, not the scales, but the magnet will have a mass, and you can measure that. And what we're going to do is as the current flows through the wire, it's going to impart a magnetic field, impart a force due to its presence in the magnetic field, because as the current passes through the wire, it's going to create a magnetic field, but it's already in a magnetic field, and so those two things are going to interact with each other. And we're either going to get a force going downwards, which if the wire is fixed in place, then, and because of Newton's third law, of course, if the magnet yoke here applies a force to the wire, then the wire must also apply a force to the magnet here. And so I'll show you how you work out which direction it's going to be in a second, but one of two things is going to happen. Either it's going to push down on the scales, or it's going to push up on the scales. Not really on the scales, but on the magnet. So it'll push down on the magnet, which will then push down on the scales. And so the scales will start reading something. Or it will push up. Now, whatever it reads, we're going to have a mass, and then if we just multiply the mass by gravitational field strength, 9.8, we'll get a force, because it is the scale is just measuring weight anyway. It doesn't actually measure the mass of an object. It will, like any set of balances or scales, it's going to measure the effect of weight on it, and then it just does a calculation by dividing everything by 9.8 to give you a mass in grams. So how are we going to know which way it's going to go? Well, let's do that first of all. So we have left and right hand rule. Left is positive. Now we're talking about current flowing through a wire, so we're talking about electron movement, and so we're going to be using the right hand here to determine the force, because it's going to be electrons. F, B and I, we're going to have our fingers at 90 degrees to each other, so we've got 90 degrees here, and we've got 90 degrees here, and we've got 90 degrees here. So 90 degrees in everyone, and so this is going to be our force, magnetic field strength, and I should have thought about this before actually doing it, because I'm going to contort my hand in an awkward way. So if my north and south is going from here to here, I'm going to be doing this, and then my current, you can see it's pointing towards me, which this is also pointing towards me, or if I'm looking at this on a screen, then this is coming towards me, and so we've got this like that, and so I'm going to have a downwards force. So this is going to, in theory, have a force going down. So let's just say that my B is here, and my I is there. So by doing this, we're going to be able to detect a force. So what we can do with this, well, we can vary the current going through the wire. So if we vary the current going through the wire and read out or calculate our different values of force, which we're going to derive from, we'll get a reading from the scale. We multiply that by 9.8, we'll get a force, and we will find that here the force is going to be directly proportional to the current. What else can we do? Well, we can vary the length of the magnets, and so we're going to have here, we're going to have the length, and we will find that force is directly proportional to length. We could swap out we could use different magnets, so we use different strengths of magnets, and we would find that force is directly proportional to magnetic induction. And finally, what we can do is we can rotate this angle. So this is going to be hard. If we have our let's see, I need a thing that's long and straight. Hold on. Okay, so what we'll have is that we will we'll vary this is coming through straight, and so what we can do is we can vary the angle at which this comes through the magnetic field at, so we can move it through various angles like this. I'm not talking about moving it sort of up and down, but we're talking about making it come through various angles. So if we're looking at this, we're looking at this end on, but if we're looking at it top down, it's going to move through angles from side to side, and we'll find out that force is directly proportional to the sine of the angle. Putting all of this together, we get our formula. F is equal to, now in the notes it's written as BIL sine theta, which is just how I remember the formula. I'll need to probably go back and change that because that's not how it is in the learning intentions. In the learning intentions, it is written as ILB sine theta. Okay, so the force is equal to current times length times magnetic induction times sine theta being the angle at which it's in there. Now, if we were to look at this, let's just do another quick drawing. So this would be a top-down projection. So that's your magnets there. Your wire is going to be coming through like this. And we're having our current in that, in this instance, coming through there. So your magnetic field is going to be, well, if we've got our north and our south, then your magnetic field is crossing like so. Now, what this formula does is you're going to have an L in here, and that L is going to be the length of the magnets. So let's have length from there to there. And one possible source of inaccuracy about this is that if you do it like this, then the magnetic field doesn't stop at the length of the magnets. What will happen is that you will have this bowing out of the magnetic field around the magnets like that. So you're going to get an inaccuracy in there. What else have I got? That's fine. And as I say, with the sine theta, if we wanted to vary that, we would sort of rotate that around this pivot point. We could rotate it this way or rotate it that way. So this inaccuracy here about the straight wire going through, what we're going to do about that is, as again you see from here, is that we bend our wire at a right angle here. Okay, so if we now, so let's say the current, instead of coming straight through, so let's just say that the current is going to go down this way. So another drawing, current is going to go down that way. It's going to go along this way. And it's going to come up that way. This is much, much easier to actually show you in real life. So your wire is bent into a kind of U-shaped. This would be a sort of side-on view. I've done that wrong, haven't I? Okay, no matter. It doesn't matter. Really, that should have been an X and this should have been a dot. But actually, yeah, let's just change that. Just a bit. Right, okay, so what are we saying? Yeah, this is going down. The current is going down that way. This is coming up. We're having a dot here. Right, so it's coming down, going along, and then it's coming back up. All right, okay. I hope you're still with me. Right, so we're using a right hand rule. Same as before, our magnetic field is going to be coming north to south. It's going to be coming through this way. That way, and so we're going to have FBI. We're turning it upside down. B going in that direction there. Our current is going there. Now, in this portion of the wire, there, when it's flat, it's having a downwards force. In this bit of the wire, as it's going down, we need to change this. And so our FBI, so B still points in that direction. This now comes here. So our B, now our wire, our current is going down that way. And so you're going to need to sit and pause this with your screen, and you're going to have to play with your hands a bit, and so that you get this right. And so you're having your magnetic field going in that direction. You're going to have your current now coming down, and you're going to have a force that is going in that direction. So force in that direction. When it's along here, the force is pushing straight down. But when you get here, again, B, now I is coming up that way, and you're going to get a force going in that direction. Now, this bit and this bit are going to be having a force like that and that, but the length of material in this magnetic field is going to be the same length. There's going to have the same current flowing through it, and so these two forces will actually cancel each other out. And so the net result of these two forces, of the bend of the bit and the wire, is it's going to have the effect of cancelling each other out. And they're acting perpendicular to the scales, and so they're not going to register on there anyway. And so this will allow us to accurately determine the length of wire that is actually in the magnetic field here. So when doing this experiment, we're always going to use a U-shaped piece of wire. I really hope that that has made some sort of sense. Because, as I say, it's an awful lot easier to show you in practice and to be sitting in front of you and playing with your hands when you're there. But nevertheless, so we have an experiment. We can determine a formula for force on the current carrying conductor. Now, in all of these cases, unless we're varying sine theta, if it's coming perpendicular at 90 degrees through the field, and then we're going to have F is equal to IL B sine 90. Sine 90 is obviously just 1, and so we're going to have, sometimes you'll see this formula is just ILB. And this is just a simplified version of the formula for occasions where it's just coming through in a straight line. Or I shouldn't really say a straight line, but coming through perpendicular to the magnetic field. Okay, so here we have a worked example, and it says, and we'll read this very carefully, and I'll explain further. I can do a diagram. So calculate the force in a horizontal conductor if the length of conductor is 5 centimeters. That's straightforward. In a magnetic field of 0.4 teslas, the current in the conductor is 8 amps, and the wire is at an angle of 60 degrees to the face of the magnets. So let's just do a very quick sketch of this. We're going to have our magnets like this. We're going to have our magnetic field coming along this way. Now it says it's 60 degrees to the face of the magnets. And so we're going to have, well, let's just say that this is going to be 60 degrees. 60 degrees in there. Now where the sine theta bit is taken, the sine theta has got to be taken from the direction of the magnetic field. And so crossing the magnetic field here is going to be 90 degrees. And so we're not actually looking for the 60 degrees, we're looking for the angle that is going to be in here. So that's going to be our theta. Now if it's 60 degrees to this line, then to this line, then it's going to be 30 degrees. So theta is actually equal to 30 degrees. And so be careful with that. Be careful that the angle that you're choosing, if it's at 0 degrees here, then there's going to be no force. If you're looking at, again, this sine 0 is going to be 0, so that it won't experience a force. And so if you place your wire that is parallel to the magnetic field lines, you'll get a 0 force. Now I know that this is not drawn very well to scale. There's no way that this angle in here is going to be 30 degrees and this is 60, but it is what it is. That's just my bad drawing skill than actually anything to do with physics. So our formula F is equal to IL B sine theta. Our current of 8 amperes times 5 centimeters times the magnetic induction, which is 0.4, times sine 30. We'll get that, and then we'll just have 8 times. And that's just going to give us 0.08 newtons. Okay, well that's the strength of the magnetic field. So the course notes on page 18, 19 detailing this, but then so have a read through them, but also on page 20, 21 it takes you through some examples of where this is used, notably in electric motor, and you also have something called an electromagnetic pump. So have a look through those course notes, and just it's a lot of wordy stuff. And that's it. I'll be in touch with some extra work now. That's the third of the 3 lessons that are dealing with magnetic fields, and everything that we need to know about that. So as I say, I'll be in touch with some questions for you to do, and an assignment which I'll post. Okay, well thanks for watching, and hope you well. Bye.